The ScioBot 2.0 vision with an ultrasonic sensor will allow us to detect and avoid objects as our ScioBot 2.0 navigates autonomously. You are going to need a fully assembled ScioBot 2.0, an ultrasonic sensor, the ScioBot Vision adapter, and 4 male to female jumper wires to connect your sensor to your breadboard. Let's now assemble the Vision components. Let's start by inserting the 4 female ends of the jumper wires into the Vision adapter. Use the slot that accommodates 4 wire terminations. This will create a plug receptacle for our ultrasonic sensor. Press the wire terminals in until they are flush with the top side of the Vision adapter. They don't need to be perfect. Next, plug your ultrasonic sensor into your newly built plug receptacle. Make sure the clip on the Vision adapter is pointing towards the back of your ultrasonic sensor. Now that our sensor is fully assembled, we can go ahead and use the clip on the back of the Vision adapter to attach it to the front of our ScioBot 2.0. You are now ready to connect the wires to the breadboard so that we can write code to interface with the ultrasonic sensor. This schematic shows what our sensor wiring will look like when we finish. The pins on your ultrasonic sensor are labeled with ground, echo, trig, and VCC. Let's start by connecting the ground pin to the negative power rail on the breadboard. Check to see which color wire is connected to the ground pin on your ultrasonic sensor and connect the other end of that wire to the negative power rail on your breadboard. The next wire we'll connect is the VCC wire. Let's connect this to the 5-volt out pin on the microcontroller. With this wire and the ground wire in place, the ultrasonic sensor is now connected for power. Now connect the echo pin from the ultrasonic sensor to pin D12 on the microcontroller. And finally, connect the trig pin from the ultrasonic sensor to pin D13 on the microcontroller. Now that we've finished our wiring, let's go ahead and fire up the Arduino IDE so that we can write some code to interface our ultrasonic sensor with our ScioBot 2.0. Start by saving your sketch. I'm going to save mine on the desktop and call it ScioBot 2.0 Vision. Feel free to save yours wherever you'd like and name it whatever you prefer. Once we've saved our sketch and given it a name, we can jump right into writing the code. A lot of this code will be very similar to the ScioBot 2.0 base code. We will begin by defining our microcontroller pins. Let's type const int motor write A equals 2 semicolon. Next will be const int motor write B equals 4 semicolon. Next we'll type const int motor left A equals 7. Following that we will say const int motor left B equals 8. Then const int enable right equals 5 and const int enable left equals 6. If you recall, we can use the enable pins to either enable or disable current flow to our motors. Remember, we connected our echo pin to pin D12 and our trigger pin to pin D13. Let's go ahead and create those constants. Next, we will need to create a few variables. We'll need one to hold the ultrasonic ping duration data, we'll need another to hold the calculated distance value, and a third to hold a random number that we'll use to make decisions. Let's type float duration, semicolon, on the next line float distance, semicolon, and on the next line long random number, semicolon. Great, we have now defined all of our constants and variables. Let's move on to writing the setup code. Let's start by defining our pin modes. In the setup function, type pin mode, open parentheses, motor write A, comma, output, close parentheses, semicolon. You can now copy this line and paste it 5 more times and change the variable from motor write A to motor write B, motor left A, motor left B, enable right, and enable left. Great job! Next, we're going to set the pin mode for echo pin to input and the pin mode for trig pin to output. Perfect. Now we have just 2 more things to do in the setup code. Let's type random seed, open parentheses, analog read, open another parentheses, 0, close parentheses, and semicolon. This will use the value returned from the call to analog read 0 to seed our random number generator. And last but not least, let's type serial.begin and in parentheses 9600 to initialize our serial monitor. Let's quickly verify our code to make sure everything looks good so far. Awesome, now we can get into the loop function to start writing the code to read the sensor data and control the robot. What we're going to do here is use the ultrasonic sensor to check the distance in front of the ScioBot. If that distance is greater than 15 centimeters, we'll continue driving forward. Otherwise, we will stop, reverse a little bit, and then we're going to generate a random number between 0 and 100. If that random number is less than 50, we'll configure the ScioBot to turn to the left. Otherwise, we'll turn to the right. Once the ScioBot has finished turning, the loop will restart from the beginning and the ScioBot will continue driving forward until it encounters another obstacle. So let's begin by writing the code to determine the distance to an object in front of the ScioBot. Inside the loop function, start by typing digital right, open parentheses, trig pin, comma, low, close parentheses, semicolon. On the next line, type delay microseconds 2. These 2 instructions will clear any electronic noise on our ultrasonic sensor's trigger pin. This will allow us to get a clean, accurate ultrasonic ping. Now let's initiate our ultrasonic ping by typing digital right, trig pin, comma, high. On the next line, type delay microseconds 10. And finally, on the next line, digital right, trig pin, comma, low. What we've done here is initiate a 10 microsecond ultrasonic ping. The sound waves of this ping will travel away from the ultrasonic sensor until they encounter an object, at which point they'll bounce back towards the ultrasonic sensor. This is where we can use the echo pin on the ultrasonic sensor to record the duration of the sound wave's journey. To do this, we're going to use the duration variable we declared earlier and type duration equals pulse in, open parentheses, echo pin, comma, high, close parentheses, semicolon. This puts our sensor in a state where it's waiting for the ultrasonic ping to return. When the ping returns to the sensor, the echo pin is set to a high state and we can record the duration of the ultrasonic ping. We can then use this duration and the known speed of sound to calculate the distance that the ultrasonic ping traveled. On the next line, let's type distance equals duration times 0.0343 divided by 2. It's a known constant that sound travels at 0.0343 centimeters per microsecond, and because we've recorded the duration of the ping traveling out and back, we divide by 2 to get the one-way distance. Let's go ahead and write the code to print our distance value to the serial monitor. Type serial.print, open parentheses, and then in quotes, type distance. On the next line, type serial.print line distance. Now all we have left to do is to tell the ScioBot what to do based on the presence of an object. Let's say if the distance is greater than 15 centimeters, we'll configure the ScioBot to go forward. To go forward, we need to set both the enable left and enable right pins to high, motor left A to high, motor left B to low, motor right A to high, and motor right B to low. Now, if the distance is less than 15, it means there's an obstacle in the way. So in our else statement, what we're going to do is we'll stop, back up, pick a direction to turn, and turn away from the obstacle. All we need to do to stop is set both enable pins to low. Let's copy this code from above and paste it into our else statement. Now change both high parameters to low. Let's stay stopped for half a second by adding a delay of 500 milliseconds. Now to reverse, we want to set the left and right enable pins to high and the left and right motors configured to reverse. Let's copy the forward code we wrote above and flip the high and low values for each motor. And let's reverse for 750 milliseconds. Now let's copy our stop code from above and paste it below to stop for half a second. Now that we've backed away from the object, we need to determine which direction we're going to turn. Let's generate a random number between 0 and 100 by typing random number equals random and in parentheses 100. If the random number is less than 50, we will configure the motors to pivot to the left. Set motor left A to low, motor left B to high, motor right A to high, and motor right B to low. If the random number is greater than 50 in our else statement, we will configure the motors to pivot right. Let's copy our left pivot code from above, paste it into the else statement, and flip the high and low values for each motor. Now that we've configured our motors to turn in their respective directions, outside of the if-else statement, let's set enable left and enable right to high. Now let's delay for 1000 milliseconds so that we turn for 1 second, and then we'll set our enable left and enable right to low to stop again for 500 milliseconds. I'm going to clean up a little formatting here and verify my code to make sure everything looks good. And fantastic! That is it. That is the rest of the code for the ScioBot 2.0 Vision. Let's use the USB cable to connect our ScioBot to the computer so that we can upload our code. Let's navigate to the Tools menu to make sure we have Arduino Nano selected for the board and that we have USB serial selected for the port. Now go ahead and hit the Upload button to upload your ScioBot 2.0 Vision code. While your ScioBot is still connected to the computer, open the serial monitor and we can see the distance data being output in real time. If there's nothing in front of your ScioBot, the wheel should be rotating forward. If you put your hand or another object in front, you'll see that it stops and executes its turnaround routine. Really great job, and I encourage you to experiment to come up with better routines to determine which direction the ScioBot should turn.